Time travel has captivated human imagination for generations, featuring prominently in science fiction and theoretical physics. But what do we truly understand about the possibility of traveling through time? Let's delve into the scientific perspectives on this intriguing concept. First of all, what is the secret of time travel?
The secret of time travel lies in the complex interplay of space and time, as described by the theory of relativity. According to Albert Einstein's theories, time is not an independent constant but is intertwined with the fabric of space, forming what we call space-time. This means that under certain extreme conditions, time can behave in ways that seem counterintuitive to our everyday experience.
Secondly, what is time travel theory and derived from?
Time travel theory encompasses various scientific ideas and hypotheses that explain how traveling through time could be possible. These theories mainly derive from Einstein's theory of relativity and involve concepts like Number 1. Special relativity proposes that time dilation occurs when an object approaches the speed of light, causing time to slow down relative to a stationary observer. Number 2. General relativity explains gravitational time dilation, where time slows down in stronger gravitational fields due to the curvature of space-time caused by massive objects. Number 3. Wormholes, hypothetical tunnels in space-time that could connect distant points, potentially allowing for instantaneous travel between them. Number 4. Quantum mechanics explores the possibilities of parallel universes and entanglement, which could theoretically allow for alternate timelines and non-local interactions.
Thirdly, types of time travel. Time travel can be categorized into different types based on theoretical mechanisms and their implications. Forward time travel is achieved through time dilation, as predicted by Einstein's theory of special relativity. When traveling at speeds close to the speed of light, or in strong gravitational fields, time slows down for the traveler relative to someone who remains stationary.
For example, an astronaut traveling in a high-speed spacecraft would age more slowly compared to people on Earth. This has been observed in experiments with atomic clocks on fast-moving jets and satellites.
And a fact we can say is that astronauts aboard the International Space Station experience time at a slightly slower rate than people on Earth due to their high orbital velocity, resulting in a time difference of milliseconds. Backward time travel is more speculative and involves concepts such as wormholes or closed, time-like curves. According to general relativity, certain solutions to Einstein's field equations suggest that paths through spacetime could loop back to the past.
For example, the idea of traversable wormholes, if they could be stabilized and manipulated, might theoretically allow for travel back in time. However, this remains highly theoretical and faces significant challenges.
Now, the fact is, the concept of a closed time-like curve was first proposed by mathematician Kurt Gödel in 1949, who showed that general relativity allows solutions where time loops back on itself. Time travel to the past introduces paradoxes that challenge our understanding of causality.
The grandfather paradox is a classic example. If a time traveler goes back and prevents their grandfather from meeting their grandmother, it would prevent the time traveler's own birth. This creates a contradiction. How could the time traveler have existed to go back in time in the first place?
Another intriguing one is the bootstrap paradox, also known as a causal loop. This paradox occurs when an object or piece of information sent back in time becomes the cause of itself existing in the first place, creating a loop with no clear origin.
Physicist David Deutsch proposed the many worlds interpretation to address these paradoxes, suggesting that any changes made in the past create a new, alternate universe, rather than affecting the original timeline.
Quantum time travel mechanism explores the interplay of quantum mechanics and relativity. Concepts like quantum entanglement and the many worlds interpretation could imply that time travel might be feasible in ways that are not yet fully understood. Example, quantum entanglement, where particles affect each other instantaneously over distances, hints at non-local effects that could theoretically relate to time travel, though this is speculative. Fact experiments with quantum entanglement, such as those performed by Alain Aspect in the 1980s, have demonstrated that particles can be correlated in ways that defy classical explanations, suggesting deeper connections within the fabric of reality.
Is it possible to be a time traveler? From a theoretical standpoint, becoming a time traveler is possible, at least into the future. Here are some key concepts.
Time dilation. Time dilation is a phenomenon predicted by Einstein's theory of special relativity. It refers to the apparent slowing down of time for an object moving close to the speed of light relative to an observer at rest. This can be explained through the following points. Speed of light. According to special relativity, the speed of light in a vacuum is constant, and the maximum speed at which all energy, matter, and information in the universe can travel. Relativity of time. As an object approaches the speed of light, time slows down for that object relative to a stationary observer. This effect has been confirmed through various experiments, such as observing the decay rates of fast-moving particles and synchronizing atomic clocks on high-speed jets. A practical example we can express: if an astronaut travels in a spaceship at 99% of the speed of light for what they perceive as 1 year, several years could pass on Earth. Upon their return, the astronaut would have aged only 1 year, while many more years would have passed on Earth. The fact of this: the twin paradox is a famous thought experiment illustrating time dilation. One twin travels on a high-speed journey into space and returns, finding that the twin who stayed on Earth has aged significantly more.
Gravitational time dilation is another fascinating consequence of Einstein's general relativity.
This concept explains how time runs slower in stronger gravitational fields.
Curvature of spacetime. Massive objects like stars and planets curve the spacetime around them, creating what we perceive as gravity.
This curvature also affects the passage of time.
Stronger gravity, slower time. The stronger the gravitational field, the slower time passes.
The closer you are to a massive object, the more pronounced this effect becomes.
This effect has been measured precisely using atomic clocks placed at different altitudes.
A practical example is clocks on satellites in orbit, experiencing weaker gravity, tick faster than clocks on Earth's surface, experiencing stronger gravity.
This difference must be accounted for in the GPS system to ensure accuracy.
And the fact of that, the pound-for-pound effect of gravitational time dilation was confirmed in 1959 by a famous experiment where two atomic clocks, one on the ground and one flown around the world, showed measurable differences in elapsed time.
Wormholes, also known as Einstein-Rosen bridges, are hypothetical tunnels in spacetime that could connect distant points, potentially allowing for instantaneous travel between them.
Here's how they might work.
Theory wormholes were first proposed by Albert Einstein and Nathan Rosen in 1935 as solutions to the equations of general relativity.
They described a bridge connecting two separate points in spacetime.
Structure: a wormhole consists of two mouths connected by a throat.
If traversable, it could allow matter to travel from one mouth to the other almost instantaneously despite the distance in normal space.
Challenges of that:
stability. For a wormhole to be traversable, it would need to be kept open by exotic matter with negative energy density, which has not been observed in nature.
Size: naturally occurring wormholes, if they exist, could be incredibly small, requiring advanced technology to enlarge and stabilize them.
Time travel. If one mouth of a wormhole were accelerated to near light speed and then returned or placed in a strong gravitational field, time dilation effects could potentially allow it to function as a time machine.
However, this remains highly speculative.
Fact of that, the idea of traversable wormholes, though mathematically consistent, faces significant practical and theoretical challenges.
Current physics does not offer a concrete method for creating or stabilizing wormholes. Who was the first time traveler? Well, the idea of the first time traveler is largely a matter of fiction rather than fact.
In literature, H.G. Wells's 1895 novel The Time Machine introduced the concept of a person traveling through time using a machine, making Wells's protagonist arguably the first fictional time traveler.
In reality, astronauts and high-speed travelers experience time dilation, making them real-life examples of time travelers, albeit on a much smaller scale.
For instance, Russian cosmonaut Sergei Avdeyev, who spent a total of 747 days in space, experienced a time dilation that caused him to age slightly less than people on Earth, effectively making him a time traveler by a few milliseconds.
What is the mystery of time travel? The mystery of time travel lies in the numerous paradoxes and theoretical challenges it presents.
Paradoxes. Time travel into the past introduces paradoxes that challenge our understanding of causality.
Grandfather paradox. If a time traveler goes back and prevents their grandfather from meeting their grandmother, it would prevent the time traveler's own birth. This creates a contradiction. How could the time traveler have existed to go back in time in the first place?
Bootstrap paradox. Also known as a causal loop, this paradox occurs when an object or piece of information sent back in time becomes the cause of itself existing in the first place, creating a loop with no clear origin.
The grandfather paradox has been a subject of extensive philosophical and scientific debate. Various proposed solutions, such as the many worlds interpretation and self-consistent history theories, attempt to resolve these issues.
Quantum mechanics. Some interpretations of quantum mechanics offer potential resolutions to these paradoxes and open new possibilities for time travel.
Many worlds interpretation. This theory suggests that every possible outcome of a quantum event actually occurs, each in a separate, parallel universe. Thus, if a time traveler changes the past, they would create a new, alternate timeline rather than altering the original timeline, avoiding paradoxes.
Quantum entanglement. Entangled particles remain connected such that the state of one instantly influences the state of the other, no matter the distance. This phenomenon hints at non-local interactions that could theoretically relate to time travel, although this is speculative at present.
The many worlds interpretation was first proposed by Hugh Everett III in 1957. It remains one of the more intriguing and controversial theories in quantum mechanics.
Nature of time. The fundamental nature of time remains one of the greatest mysteries in physics.
Block universe theory. This theory posits that past, present, and future all coexist simultaneously, suggesting time is like a block that we move through. This view supports the idea that time travel could be possible if we could move freely within this block.
Dynamic time. Conversely, the more intuitive view is that time flows from the past to the future, with the present being a moving point. Understanding the true nature of time is crucial for comprehending how time travel might work.
The concept of time as a dimension akin to space was revolutionized by Einstein's theories, which showed that time could be stretched and compressed, similar to spatial dimensions. Historical context and notable contributions to time travel theory. The concept of time travel has deep roots in both science fiction and scientific theory.
H.G. Wells. The notion of time travel first gained widespread attention through literature. H.G. Wells's novel, The Time Machine, published in 1895, popularized the idea and introduced many to the concept of traveling through time.
Albert Einstein. Einstein's theories of special and general relativity, proposed in the early 20th century, provided a scientific basis for time travel, especially through the concept of time dilation.
Nathan Rosen. Collaborating with Einstein, Rosen co-authored the paper on wormholes, proposing the theoretical existence of passages through space-time that could facilitate time travel.
In modern times, many physicists continue to explore and challenge the boundaries of time travel theory.
Kip Thorne. An American theoretical physicist, Thorne has extensively studied the properties of wormholes and time travel. His work has popularized the idea within scientific communities and contributed to public interest.
Stephen Hawking. Renowned for his work on black holes and cosmology, Hawking proposed the chronology protection conjecture, suggesting that the laws of physics prevent time travel to avoid paradoxes.
Current research. Scientists at institutions like CERN and various universities around the world continue to investigate the fundamental nature of time and the potential for time travel, exploring new theoretical frameworks and experimental possibilities.
Time travel remains one of the most intriguing and complex concepts in both science fiction and theoretical physics. As our understanding of the universe evolves, who knows what new insights might emerge about the nature of time and the possibilities of traveling through it. Curious about the latest in science and technology? Don't miss out. Subscribe to our channel, like this video, and hit the bell icon to stay updated on our exciting explorations into the mysteries of the universe. Share your thoughts and theories about time travel in the comments below. Until next time, keep exploring the unknown.